lecture number 6. Now in the previous lecture we have discussed about the heating of an electrical motors. Now come to the cooling of the motor. Cooling of an electrical motors. Now similar to the heating characteristics, let's say the motor is achieved already a steady state temperature of theta equals to say theta SS, which is equals to theta 2. From this the motor is to be stopped, and accordingly the power of the motor will be shut down and the motor heat will be dissipated to the cooling medium. Now if the load is thrown off, the motor is now cooled down from this temperature theta 2, which is already achieved before the load is switched off. Now say heat loss will reduce, heat loss will reduce, heat loss will reduce to a small value, say P1 dash. Okay, and the heat dissipation constant, new value of the heat dissipation constant is say K2 dash. Previously for the heating we have considered this power is the P1 and this heat constant is K2. Okay. Now similar equation for the cooling will be takes place, that is K1 d theta dt. Again I am writing the first order differential equation. Now P1 replaced by the P1 dash minus K2 replaced by K2 dash theta. Okay. Now solving this first order differential equation, solving first order differential equation, considering initial temperature is theta 2, from which the motor power is shut off at t equals to 0. Okay. Then theta becomes, this is the new steady state value, theta SS dash. Okay. 1 minus e to the power minus t by tau dash, new time constant for the cooling, plus the initial temperature is theta 2 e to the power minus T by tau dash. Okay, same equation where theta SS dash becomes P1 dash by K2 dash, and the time constant tau dash equals to K1 by K2 dash. Okay. Now this is the cooling equation of the motor. Now if the motor is disconnected, entirely disconnected, not some amount of load is switched off or thrown off, entirely disconnected from the supply, what will happen if the motor is disconnected from the supply? Then P1 dash will be equals to theta SS dash equals to 0. Okay, all terms becomes 0. Then putting all these values, steady state temperature becomes 0, P1 dash, that is the power, will be 0. Then we can write theta equals to theta 2 e to the power minus T by tau dash. Okay. Now from which, if I substitute put T equals to tau dash, then what will happen when the motor is disconnected from the supply? Theta becomes theta 2 into this term becomes 0.368, that is 36.8% of theta 2. Okay, that is, you can say the cooling time constant will be defined as when the motor is cooled up to 36.8% of its initial temperature rise. That is, the cooling time constant is defined as the machine as the time required to cool the machine, as the time required to cool the machine to 36.8% of its initial temperature rise. Okay. Now if I draw the heating cooling characteristics, then it looks like this. T Now this is the exponential in nature, heating, and cooling is also exponential in nature. Okay. This part is heating, and this part is cooling of the machine. Okay. Now based on this, we will select the power rating of the machines. Now come to the classes of motor duty. Classes of motor duty and selection of power rating. And selection of motor power rating. Okay. Now first one is the continuous duty. Continuous duty, where motor is required to operate for large or long time period, where the steady state temperature of the machine will be achieved entirely. That is, if I consider a constant load torque on the machine, this is the constant load torque TL, and corresponding temperature rise of the machine becomes exponentially and finally achieved steady state value. Okay. Now different kind of continuous duty machines will be there, or different kind of continuous motor operation will be there. That is for constant load torque, constant load torque. Previously we have discussed when the equivalent inertia and torque will be considered. The motor can drive linear motion of the load torque as well as the rotational motion of the load torque. For constant load torque, the size of the machine or the power rating, whatever it may be, size of the machine can be determined as follows. What are that? For rotary motion or rotational motion. For rotational motion. Then P equals to, you can write, this is the output power. P out will be equals to TL into the speed omega m, that is TL into 2 pi n by 60. Now what is the input power of the machine? This is TL omega m by efficiency. Okay. It is P out by efficiency basically. Then you can write TL into 2 pi n by 60 into 1000 to convert it in kilowatt. This amount of kilowatt, okay, is roughly approximately TL, sorry, eta will be there. TL n divided by 9550 eta. Okay, that amount of kilowatt for the rotational motion. Now come to the linear motion. Now for this rotational motion, generally the V belt drive will be, or the some others kind of load is considered. Okay. Now for linear motion, P equals to F into, F is the force, 9.81 into V divided by eta into 1000. Now this becomes F into V divided by 102 multiplied by eta, this amount of kilowatt, where F is the force in kg, and V is the velocity, linear velocity in meter per second. Okay. Now C for hoist load. This is same as the linear motion, but equation will be slightly modified because of the counterweight. Okay, that is motor will be drive motor will drive the linear body of the lift as well as the counterweight. Okay, that's why this power equation becomes half. That is P becomes FV divided by 2 into 100 to eta. That is kilowatt. Okay. D for pump load. P becomes Q rho H divided by 100 to eta in kilowatt, where Q is the Q is the discharge of the pump or delivery by the pump, meter cube per second. Rho is the density of the liquid in kg per meter cube, and h is the height or gross head in meter. This gross head will include the head static head as well as the friction head. Okay, both is considered here. Now come to the number 2. If the load is fluctuating, or intermittent load. Now in this case, the load is continuously varying in nature. Okay, that is, if I draw the load characteristics, it looks like this. Say current. If I draw the characteristics of the load current, say this is I1 is operating for time t1. Now after that, after sometimes after time t1, the current becomes, load is increased, current will be increased for time t2. Now consider that load is decreased for time t3. Again it is increased I4 for the time period t4, and up to, say this is IN for time Tn. Okay, this is the load curve. Now there are several methods to obtain the motor power rating. Number 1, for fluctuating kind of loads, method of equivalent current. Now motor loss will consisting of two parts. Motor loss P will consisting of two parts. One is P loss, one is constant loss, which includes core loss plus friction windage loss. Another part is the copper loss, that is I square R loss. Okay. Now constant loss will not vary or will not depending upon the load, but copper loss will be varied accordingly the load characteristics. That is, we can write, say, if the equivalent current, if equivalent current of the machine is IEQ, then we can write from here PC plus I equivalent square R will be equals to PC plus for the first operation up to time t1 I1 square R t1 plus PC for the time t2 and so on up to nth time in square R, this is t2, this is tn, whole divided by the total time, that is t1 plus t2 plus up to tn. Okay. Now if I split this equation, that becomes PC in all the time period. PC is constant, the energy will be PC multiplied by T1 plus T2 plus up to Tn plus I1 square R to be taken as common because motor resistance is constant. I1 square T1 plus I2 square T2 plus Tn multiplied by R. Okay, whole divided by Tn. Okay, that is the first term becomes PC plus the next term will be I1 square T1 plus I2 square T2 plus In square Tn multiplied by R divided by the total time T1 plus T2 plus Tn. Okay. Now if I compare the left hand side and right hand side of the equation, PC will be cancelled out, then RR will be cancelled out, I equivalent becomes root over I1 square T1 plus I2 square T2 In square Tn whole divided by T1 plus T2 up to Tn. Okay. This is the method of the equivalent current to find out the power rating of the machine. Now similarly, another method can be applied since the motor torque is depending upon the motor current, then we can also find this equation from the equivalent torque method. Okay, that is B. Equivalent torque method. Now same as the equivalent current, the torque equivalent becomes, we can write, since the torque is depending upon the motor current, T1 square, T1, T2 square, T2, Tn square, Tn, all divided by T1 plus T2 plus up to Tn. Okay. Now, if the motor speed is constant or the variation of the speed depending upon the induction of the load will not vary much more, then we can consider the constant speed operation, and for that power equivalent power method can also be applied to find out the motor rating. Equivalent power method. When it is applied at constant speed operation. Okay, the equivalent power from where we can directly select the motor power rating. Same thing, P equivalent P1 square T1 plus T2 square T2 up to Tn square Tn. T1 plus T2, that is the total time. Okay. Now for the fluctuating kind of loads, we can determine the motor power rating by these three methods. Okay. This is the equivalent power method, equivalent torque method, or equivalent current method. Okay. Thank you.